Welcome back to the class on a power semi-connected drives. In this lecture, we are going to discuss about the numericals on a induction motor part 2. Here, we are going to solve the two more numericals, which is based upon the V by F control of a induction motor. So, let me take up the first numerical. A Y-connected spiral case induction motor has the following parameters: 400 volts, 50 Hz, 4 poles, 1370 RPM, stator resistance 2 ohm, total resistance referred to the stator 3 ohm. Stator leakage reactance equal to the rotor leakage reactance referred to the stator, that is XR dash, equal to 3.5 ohm. Motor is controlled by a voltage source inverter at a constant V by F ratio. The inverter allows frequency variation from 10 Hz to the 50 Hz. Calculate the values of the following. Apply the plot between the breakdown torque and frequency. That is the first one. So omega S value Ns equal to 20 F by P. The frequency is given 50 Hz, number of poles is given 4 poles, substitute all the values. Omega Ms, nothing but a synchronous speed in radians per second equal to 2 pi Ns by. So what are the value got here that you have to take here? So finally you're getting the value 50. Right. Suppose here we are maintaining the V by F ratio is constant. Here we have taken one constant K value. That value will be vary from 0 to 1. Now we are going to take the K into F. Nothing but as the K value is vary from 0 to 1, this frequency value also will be vary from 0 to the rated frequency. So here, suppose if you take the K value 0, then the frequency will be 0. The K value is 1, then the F equal to rated frequency. So in that manner, we are going to take the K value such a way that how much frequency we want. To maintain the V by F ratio, proportionally you have to change the V also. So how much constant you have to take the same constant value, nothing but kV. So for a frequency K times the rated frequency, if the V by F ratio constant, the voltage is the kV. In terms of K, we are writing 3 by 2 into K omega ms times the frequency you have taken into K square V square by Rs plus square root of Rs plus K square into Xx plus XR dash whole square. So why you got the value of K here means in place of frequency you have to substitute the Kf, in place of voltage you substitute the Kv, then you are getting this equation. So now you take the K outside in the denominator here. This K square in numerator K square will be get cancelled. Finally you are getting the 3 by 2 omega ms into V square by Rs by K plus square root of Rs by K whole square plus Xx plus XR dash whole square. Here it is given that it is a star connected. This is the phase voltage. What are the voltage given in the numerical? That is the line voltage. So this voltage divided by root 3 whole square, we are getting the numerator value. The same manner, what are the values are given in the numerical? All these values you have to substitute here. Finally, you are getting the T maximum equal to 509.296 by 2 by K plus square root of 2 by K whole square plus 40. Now here we are changing the value of K. As the K is changing, we are going to calculate the K value. You can change from 0 to 1. So by changing the K value, how the frequency will be changing and maximum torque development and induction motor will be changing, that we are going to calculate. As K value is equal to, here we have taken value from K from 1 to the 0.2. Corresponding frequency 50 Hz, 45 Hz, 40 Hz, 35 Hz, like that we are getting up to the 10 Hz. The same manner, if we take the K value here, 1, the maximum torque developed in induction motor is 54.88 Newton meter. The same manner 0.9 if you take it, like that we are going to calculate all the values. So we are getting the different values of K, we are getting the maximum torque development in induction motor. Now we are going to take the frequency on the x-axis, the maximum torque development induction motor on the y-axis. So from this table you can say very easily that as the K value decreases, the maximum torque development induction motor also will be the decreases. See, this is the same thing we are going to draw in the graph. So in this manner, the maximum torque development induction motor. Since the minimum frequency available is 10 Hz, the motor has to be started at a 10 Hz. This is the expression for the torque development induction motor based at the starting, because at the time of starting the suppose induction motor is S equal to 1, we take the s equal to 1, then you have to substitute that value in a general expression, we are getting this expression. Substitute all the values. This is the value at a 41.29 Newton meter. This is the starting torque developed in induction motor. We apply the rated voltage and rated frequency. So this is the expression for the starting current taken by the induction motor. This is not a T, this is I. This is starting current taken by the induction motor at a, if you apply the rated voltage and the frequency. Substitute all the values, you are getting the 26.89 ampere. Now we are going to compare, if you apply the rated voltage and frequency to the induction motor, how much is the starting torque, how much is the starting current. If we apply the 10 hertz of frequency corresponding voltage to the induction motor, how much is the starting torque and how much is the starting current. With the variable frequency control, the constant V/F ratio, the frequency is k times the rated value, and the voltage also will be the k times the rated value. Now T starting equal to, in terms of k, 3 by 50 pi into V square by RR dash by k divided by RS plus RR dash by k whole square plus XS plus XR dash whole. So this is the torque developed in induction motor expression at the time of starting. This is the expression for the induction motor at the time of starting is the variable frequency. K is representing the variable frequency constant. Now in place of K, now we are going to take the constant value. The constant value should be represented with a frequency is 10 Hz. For 10 Hz, K equal to 10 by 50, that is equal to 0.2. Substitute the K value in the above expression, we are getting a starting torque developed in induction motor 22.7 Newton meter. Starting current taken by the induction motor, that is 8.895 amperes. These two values are representing the, if you start the induction motor with a 10 kilohertz of the frequency and corresponding voltage also, so that V/F ratio is a constant. Now we are going to take the ratio between the starting torque developed in induction motor at a 10 hertz to the rated frequency. We are getting the 0.594. The same manner, we are going to find out the ratio between the starting current taken by the induction motor at a 10 hertz to the rated frequency. If you apply to the induction motor, that we are getting a 0. Nothing but the starting current developed in induction motor also will be decreasing, as well as the current taken by the induction motor also will be decreasing if you apply the less amount of voltage to the induction motor at a start. Now we are going to solve the one more numerator. The star connected spherical induction motor has the following rating. The parameters are the 400 volts, 3 Hz, 4 port, 1370 RPM. Stator resistance is 2 ohms. Rotor resistance referred to the stator is 3 ohms. Stator leakage reactance is equal to rotor leakage reactance referred to the stator, that is 3.5 ohms. The motor is controlled by the voltage source inverter at a V/F ratio. The inverter allows the variation from 10 Hz to the 50 Hz. For a regenerative braking operation, inverter is fed from induction motor drive. Determine the following values of first one, speed of frequency of 30 Hz at 80% of the full load. The frequency of the speed is 1000 RPM and full load. The torque for frequency of 40 Hz, speed is of three different things we have to calculate in a regenerative braking. Increase in a speed from no load to the full load. How we are going to calculate this value? Ns equal to 120 F/P. We are getting the 1500 RPM minus 1370. We are getting the. Now increase in speed from no load to 80% of full load. That is equal to 0.8 times this value. We are getting the 104 RPM. The synchronous speed at a 30 Hz equal to 30 by 50 into 1500, because the synchronous speed is directly proportional to the frequency. So we are getting the 900 RPM at this value. Now the speed of induction motor at a 30 Hz frequency equal to 900, the synchronous speed plus this value are getting the 1004 RPM. So why we are adding here means it is a regenerative braking. Always the rotor speed is more than the synchronous. The frequency of speed of a 1000 RPM and full load torque. The synchronous speed equal to 1000 RPM minus at a full load, the increase in speed is 1300 RPM. So 1000 minus 130, we are getting the 870 RPM. This is the synchronous speed. Now we are going to calculate the how much frequency. Now this value equal to the P ns by 120, substitute all the values and getting a 29 Hz. The torque for the frequency of 40 Hz and the speed of 1300 rpm. Now at a 40 Hz, the signal speed equal to substitute all the values 120 FFP, we are getting a 1200 rpm. Now increase in speed from no load is equal to 1300 rpm minus 1200 rpm. This is the actual speed of a rotor. In regenerative braking, the rotor speed is always greater than synchronous speed. So increase in speed from this value minus this value is getting a 100. Now the motor torque equal to, there is an increase in speed 1000 rpm. At this value of increase in speed, how much is the torque is developed in induction motor? Minus 100 by 1300. This is the increase in speed at a full load into the full load. For the same data already we calculated previously. How much is the full load torque developed in induction motor? You take that value here and substitute all the values, you are getting the finally minus 19.51 Newton. See here why you are getting a minus means here it is a regenerative braking operation of an induction motor. In both regenerative braking and dynamic braking, motor works as a generator. In two braking methods, inverter fed induction motor differs only the way the braking energy is disposed of. Nothing but in regenerative braking, the energy will be given to the supply. In dynamic braking, the energy will be wasted across the external system. Thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box section. YouTube channel so that I am always available to answer.